Alright, so let's continue on here. The fundamental theorem of linear algebra just points out a pattern that you might have already noticed in the previous half dozen examples I showed you, which is simply this. If we have a function from Fn to Fm, then it's a linear transformation if and only if you can write it as a matrix multiplication. Alright, so this direction I already proved, and well, I mentioned it. Here's a proof. So if we suppose that the function has a formula which is given by matrix multiplication, if L of x is equal to Ax, then if you pick x and y, n vectors over f, and c is scalar, then if we look at L of cx plus y, well, that's a times cx plus y, which by properties of matrix arithmetic is c times ax plus ay, which is c times L of x plus L of y. Consequently, that gives us additivity and homogeneity. That gives us linearity of L. So there we go. That's the converse direction of this biconditional up here. And then the forward direction is actually a little bit less trivial. It requires us to begin our study of what's called the standard matrix. So if we have L, a linear transformation from Fn to Fm, I can make up this matrix. I can say, I'm going to make an n by n matrix like so. I'll feed L the first standard basis, the second standard basis, all the way out to the nth standard basis. Each one of these is an Fm output, which makes their m rows, and there's n columns by construction, so it's an m by n matrix. And I can show pretty easily that Ax is equal to L of x if we construct A like so. Here's the proof. So A times x, by definition, is A times, that's my A, times that. But this matrix times that column is, of course, a linear combination of the columns. But I can pull the weights out in front into the linear transformation using homogeneity, pull the x in, pull the x2 in, pull the xn in. And then by additivity, I can combine them by additivity, repeatedly applied. I get that, which is L of x, so Ax is equal to Lx for all x, which is to say that the formula for L is given by matrix multiplication, and that folks, is the fundamental theorem of linear algebra. Now, you know, we could just as well have derived. You know, I could show you a short derivation of where that matrix came from. It wouldn't be hard. You know, if we have L linear transformation standard basis and the E bar standard basis for the range, well, actually I didn't really need the range basis here just yet. So let me not get into it today. Well, not yet anyway. L of x is equal to that, so we just break up x as the sum over the standard basis, pull the homogeneity to pull x out. I'm basically just undoing the proof I just did to show you why that standard matrix has to be what it is. Which brings us to this, but then again, this is a linear combination of those vectors, so we can rewrite that as a matrix column multiplication like that, and there you go. That's why this has to be the standard matrix for L, right? And our notation for this is the standard matrix of L. All right. That said, well, here's an example. Well, here's the definition, I should say. Then I'll get to the example. Sorry about that. So the definition, we have a transformation from Fn to Fm. Then we define the standard matrix to be this. We just take each column, first column is T of E1, second column is T of E2, nth column is T of En. That gives us an m by n matrix corresponding to a linear transformation. So here's an example. T of xy equal to x plus y, 3y minus x. And so on the one hand, I could just look at, feed at E1, feed at E2, 1 minus 1, 1, 3, bam, standard matrix. But honestly, folks, I don't really think about it that way. What I usually do is just write out the formula like this. So this is really x plus y minus x plus 3y written in the column notation. And then I go, so that's this, right? Because I know how to multiply matrices times columns. And so, bam, standard matrix. Here's another example. So here we have, sorry about this, I gotta scribble. T of x, y, z, x plus z, y plus z, 3x, x plus y plus z. So this is a transformation from F3 to F4. You can make it R3 to R4 if you like. If I rewrite that as a column, then I'm looking for a 4 by 3 matrix. Notice it goes flippy-floppy of what you might naively expect. And there it is. So 1, 0, 1 times xyz gives me x plus c. 0, 1, 1 times xyz gives me y plus c. 3, 0, 0 times xyz gives me 3x. 1, 1, 1 times xyz gives me x plus y plus c. And that's it. That's the standard matrix. All right? Okay. So what can you say about standard matrices? What are their structure? So here's the theorem. Actually, I'd rather me have half a brain and just use my notes for a second here. So here's their properties. If we have linear transformations T and S, then the standard matrix of the sum is the sum of the standard matrices. The difference of the difference of the transformation, the matrix of the difference is the difference of the standard matrices, and you can pull scalars out. All right, nothing terribly shocking there. What's a little bit more exciting, though, is the following theorem. If we have S, all right, a linear transformation, let's say from Fp to Fm, and if we have T, a linear transformation from Fn to Fp, so I can compose these, right? Then I had to pick a different marker. This marker is way too fat. Let's see. S composed with T is a linear transformation from Fn to Fm. So we proved last time in the abstract that the composition of linear maps was a linear map. So we already know that S composed with T is linear. If I'm assuming S and T are linear, it follows that this is linear, right? So here's the same. Then S and T linear imply S composed with T linear. And here's the punchline, which I will write in a marker, which actually allows me detail. The matrix of S composed with T is in fact the matrix of S times the matrix of T. And in fact, this explains, in retrospect, why we defined matrix multiplication as we did. Okay, so let's work on this. Let's see if we can work it out. So again, the linearity of the composite's not, we already know that. If these are linear, then the composite's linear. We proved that last time. So let's look at the standard matrix. What is the standard matrix of the composite? Okay, what is S composed with T? Well, remember that is S, so S composed with T of E1, right? S composed with T of E2, and then however many we got. Let's see here. Well, S composed with T goes from F, so it starts out with T. T goes from N to P, then we go from P to M. So this is going to be a M by N. Got N columns, so our last column is the nth one. All right, so what is that? Well, that is S of T of E1. I'll skip the second one, save myself some writing. S of T of En. Great. All right. Then what? Well, simple. Look, so by the fundamental theorem of linear algebra, that is the matrix of S times T of E1, right? The matrix of S times T of En, right? But then I applied the fundamental theorem of linear algebra for S. Now I'll apply the fundamental theorem of linear algebra for T. So this is going to be fundamental matrix of S, fundamental matrix of T times E1, fundamental matrix of S, fundamental matrix of T times En. But you see, what is that? Well, by the column-by-column multiplication rule, that's matrix of S. You notice we've got a common factor of this all the way across. And so we can pull it out by the column-by-column matrix rule, and then that's just E1, and then so forth and so on. I mean, this is, of course, you know it, you love it, the identity matrix. And so there you go. That proves that the standard matrix of a composite is the product of the standard matrices being composed, which is actually, by the way, why we define matrix multiplication as we did. Now, if you look at the proof in my notes, it looks rather different, right? Because I actually sorted through, I chased indices, and I looked at it at more of the component level, and so it's kind of uglier, but it might be instructive. I mean, it will be instructive for you guys to work through that. It's not high on my priority list for you, but if you're a person who really likes the index stuff, you might enjoy it. And you might find a typo, who knows? Okay, so that's it for the column stuff. I will pick up again. So the next on the list is to come back to the discussion of isomorphism and continue on this story of matrices, talk about how you find the matrix for a transformation not of column vectors, but of an abstract vector space. There we need to bring in bases again, and so it's going to be interesting. Thanks, guys.